Hello everyone, this is Liting Hu. Today I'm going to talk about DART, our scalable and adaptive edge stream processing engine. IoT applications such as self-driving cars, interactive gaming, event monitoring have a tremendous potential to improve our lives. These applications generate a large amount of sensor data every second. On many time-critical scenarios, these massive data streams must be processed in a very short time to drive actionable intelligence. However, today most IoT applications adopt the server client architecture. So let us see this figure. The IoT sensors transfer data by using edge gateways and routers and then send back to the cloud for offline analysis. So the long distances between the sensors and the cloud may cause many issues. For example, the high latency may cause results to expire. The network infrastructure may not be able to afford these massive data streams. It is expected in 2025 there will be over 40 billion connected IoT devices generating over 79 zettabytes of data. So we have different thoughts. Can we apply stream processing technicals to the edge infrastructure? So the key idea of edge stream processing is to move the computation from the cloud to the data sources, that is gateways and routers for processing. Then data streams can be continually generated and analyzed in near real time. As shown in this figure, we have sensors continually generate streams that carry timestamps. And these streams are consumed by a stream processing engine. This engine creates a logical topology of edge nodes in a directed acyclic graph. Process tuple as they flow through the topology and outputs the results for the cloud in real time. The source nodes are sensors, the sink nodes are actuators or message queue to the cloud, and the inner nodes are edge gateways or routers that run stream operators such as map, reduce, join, filter, or machine learning algorithms. Edge stream processing will have many interesting use cases. For example, for the future intelligent transportation system, all cars will be equipped with internet access. On the front end, each car generates a lot of data streams from LiDAR, radar, camera, cell phones, and many onboard sensors. On the back end, many IoT stream applications can concurrently run on top of these live data streams to create insights and make actions. Examples include peer-to-peer service for traffic control or car sharing safety systems. Here we list several applications in the right. Note that many of these services cannot be completed on onboard computers within a single car. Instead, it requires the cooperation of many computers, edge routers, gateways, within sensors and actuators as source and sinks. So, and here's our goal. Our goal is to build a scalable and adaptive edge stream processing engine for these IoT stream applications. We aim to achieve the following goals. First, the system is expected to have a good performance in terms of quick topology, deployment, and low query latency. Second, the system is expected to scale well with the large number of concurrent running applications that have diverse topologies. And third, the system is expected to adapt well to the edge dynamics and recover from failures. However, we are facing significant challenges to achieve these goals. So the first challenge to build this edge stream processing engine is how to scale to the large number of concurrent running IoT stream applications. Due to the fast growing of new IoT sensors and devices, the number of concurrent running IoT stream applications will be significantly large. However, existing studies such as Storm, Flink, Spark most inherits the centralized master-slave architecture. as shown this left figure. So the central master is managing all applications. The responsibilities includes accepting new applications, passing DAGs into stages, mapping operators onto nodes, and monitoring their status. It may run well in the cloud. However, when it comes to the edge environments where there are many concurrent running applications, this centralized architecture may easily become a scalability bottleneck. This is because they most use a first come, first serve approach to deploy applications, which cause the application to wait a long queue and thus leads to the high deployment latency. And the second, they limit themselves to a fixed execution model and lack the flexibility for data flow path planning. And we have the second challenge. The second challenge is how to adapt to the edge dynamics. IoT stream applications runs in a very high dynamic environment. Unlike the cloud servers, edge nodes live or fail more frequently and unexpectedly. And unlike cloud servers, edge nodes have very limited computing resources, such as few core processors, a little memory, little permanent storage, and no back pressure. So therefore, the previous technicals used for the cloud, such as reallocating additional resources or buffering the data at data sources, cannot apply to the edge environments. And here is our solution. So the key innovation of the Dart design is that in sharp contrast to existing stream processing systems, in the Dart system, there is no monolithic master. Dart involves all peer nodes to jointly make operator mapping decisions, thereby revolutionarily improving scalability and adaptivity. The novelty is that we use distributed hash table-based peer-to-peer overlay networks to decompose the system architecture from 1 to N to M to N. So this is very similar to what we did in BT Towers. In BT Towers, there's no clients and servers. Everyone has the same duty. If someone downloads a file, the file is downloaded from many other nodes in the system that already have the file. At the same time, you may also upload the file to others which ask for it. So many machines work collaboratively to undertake the task of downloading and uploading files. So similar to it, we will enable distributed nodes in the Dart system to work collaboratively to undertake the task of the original single masters. Here is the Dart system overview. Dart consists of 3 layers. The first layer is the DHT-based consistent ring overlay. All edge nodes, such as routers, gateways, and power sensors, are self-organized into a DHT-based overlay. Each node is assigned a unique load ID in a large circular load ID space. Load ID is used for routing the stream data. It is guaranteed that no matter where the data is generated, the data can be routed to any destination nodes within all login hops. The second layer is the dynamic data flow abstraction. The key innovation is that we leverage the DHT-based routing protocol to approximate the path between the source nodes and the sink nodes, which can automatically place and chain operators to form a data flow graph for any stream application. The third layer is the scaling and failure recovery mechanisms. Every node has a routing table and a leaf set. The leaf set contains physically closest nodes to these nodes. We use the leaf set nodes to scale up and out operators and replicate operators to handle failures and stragglers. Here we use an example of the process of building the dynamic data flow graph for an IoT stream application. So it has 3 steps. First, we organize distributed edge nodes into peer-to-peer overlay networks. Second, given a stream application, we map the source nodes to the sensors, we map the sink nodes to the IoT actuators. Third, we enable every source node to send a join message towards the key. The key is the hash of the sink node's node ID. Because all source nodes belonging to the same application have the same key, their information will converge to a joint point that is the sink nodes. Then we keep a records of the nodes that this message passing through during routings, link them together to reversely form the data flow graph for this application. For the elastic scaling mechanism, the challenge is that how to auto-scale applications operator to adapt to the age dynamics. Our solution is that we design a heuristic approach that considers many factors. If it is a computational bottleneck, we scale up and down to increase or decrease the number of instances within a node. If it is a bandwidth bottleneck, we are going to scale out to initiate new instances on another node to increase the network path diversity. And for the failure recovery mechanism, the challenge is that how to resume the processing without losing intermediate data. There are many approaches such as replication and checkpointing, and our approach is to use erasure codes. The larger the memory space is divided, replicated, and checkpointed to each node's leaf set nodes by using erasure codes. Once any failure happens, the backup nodes will take over and retrieve the state fragments from a subset of the leaf set nodes to recompute the states and resume the processing. And there's no central master to enable this failure recovery mechanism. And here's the implementation of the Dart system. Instead of implementing the Dart system from scratch, we implement Dart on top of Apache Flume and Pastry software stack. Flume is a distributed service for collecting and aggregating large amount of streaming data, which is widely used in Kafka and Spark ecosystem. Pastry is a DHT overlay network, which is widely used to many peer-to-peer applications such as Bitcoin and BitTorrents. And we leverage their excellent runtime system, routing, substrate, and event transportation layer to implement the Dart system. And here's the overview of the Dart system implementation. The Dart system has two components, a set of distributed schedulers that span geographically zones and a set of workers. Unlike traditional systems that manually assign static scheduler or workers, Dart will dynamically assign loads as schedulers and workers. When a new application joins, needs to look for the nearby scheduler by using the Gaussian protocol. If there's no nearby scheduler, the system will create a new scheduler in that zone. We deploy a large number of applications simultaneously to demonstrate the scalability of our system. We compare Dart with EdgeWise and Storm. A result showed that Dart significantly reduced the queue wait time and deployment time, especially when handling a large number of concurrent running applications. The gap increases as the number of concurrent running applications increase. So this is because unlike EdgeWise or Storm, so this EdgeWise and Storm, they both use a centralized architecture. Their queue waiting time and deployment time increase linearly as the number of applications increase. In contrast, Dart avoids scalability bottleneck because Dart's decentralized architecture does not rely on any centralized master to deploy dark and analyze darks. So to conclude, to our knowledge, Dart is the first of its kind fully decentralized edge stream processing engine is leverage distributed hash table-based peer-to-peer overlay networks to create a decentralized architecture. It builds a dynamic data flow abstraction to automatically place, chain, scale, and recover stream operators. Therefore, it has a great potential to explore extreme scalability. However, there are also many unsolved challenges. For example, how to optimize the data shuffling service, how to adapt to the edge network's heterogeneity and hardware heterogeneity. And all of them are very interesting questions to explore further in the near future. Thank you very much for listening to this talk.